So this problem is a slab that's uniformly loaded, and we have a ball connection at B and C, and at A there's a pin connection. So a 3D pin connection, we call it a ball and socket. So there's a ball here and the socket. It resists movement in all the directions, X, Y, and Z. So our coordinate system is shown here, X, Y, and Z. Z, Y, X. And at B and C there's a ball. So the ball resists movement only in the Z direction. Then for the ball and socket, we have resisting movement in X, Y, and Z. So if we were to draw a free body diagram here, we're going to set up the body like this. Then we can have C shown here. We'll call this CZ. A B reaction shown here, BZ. These are the axes. And at the A, we'll have AZ, AY, oh, sorry, that's an AX, and AY. And the uniformly distributed load will cause the load right in the middle of the slab at here, and we'll call this 16 pounds because that's 4 feet by 2 feet, and there's 2 pounds per square foot. That ends up with 16 pounds. So we'll have 16-pound load right in the middle. And we have our dimensions. So this would be 1 foot. I can do a different color. 1 foot, 1 foot, 4 feet, and from here to here, it's right in the middle. So this will be 2 feet. So to do 3D moments, we're going to use the right hand rule. We are needing to find the reactions at the ball supports BZ, CZ, and then all the reactions at A. For moments, we're using the right hand rule. So let's visualize taking the moment at the x-axis. So let's say sum of moments at x-axis equals 0. So we're looking along this x-axis, or this edge right here. We're taking all the forces and the perpendicular distance towards that edge. And then the direction of that moment will determine with the right hand rule. So the first one, let's try looking at this 16 pounds and the distance towards that axis, which will be 1 foot. So we have 16 pounds times 1 foot. And we need to know the direction of this. So using the right hand rule, I'm going to curl my hand this way. So my fingers are in the same direction as this arrow pointing down. If it's my right hand, my thumb is pointing this way, and the thumb direction will show that it's pointing in the negative x direction, like that way. And the curl of the fingers shows that it's going, well, we can call it this direction, not necessarily clockwise or counterclockwise because now we're in 3D, but you can see that we'll have a moment this way and the curl that. So we can say that that M is happening. So that will be a negative 16 times 1 foot because it's pointing towards the negative x direction. The next force we can look at is the CZ, then we'll do BZ. These AX, AY, and AZ, they are touching the x-axis. There's also 0 perpendicular distance, so they will be not put into this calculation. So we have CZ times that 1 foot. That's 1 foot towards the x-axis also. We're looking at the direction again. So with the right hand rule, the fingers curl upward like this, and your thumb will be pointing out that way now with the right hand. So I always start with my wrist or my elbow at the axis again, then go outward towards the force. The force is the direction of my fingers pointing up. Then my thumb will show me the direction of the moment, which is to this way, towards me. That's the positive x-axis, so this will be positive. So we'll do plus CZ times 1. And the last thing is BZ, and the distance from BZ to the x-axis is 2. So we'll do BZ times 2 feet. All of that equals 0. The direction of this, it'll be starting from the x-axis this way. My fingers curling up again, and my thumb pointing out this way. So it's positive x-axis direction. Okay, we set up the moment at x equals 0. Let's set up the moment at y equals 0. So along the y-axis now. For that, we have the same forces. We're ignoring AX, AY, AZ because that's touching the y-axis, so this axis. And the distances are going to be this 16 times 2 feet. Sorry, that's not the right hand. Sorry, this is the right hand, going to the positive y. Okay, so that means positive 16 pounds times 2 feet. The next one is BZ. So BZ is going to be curling my fingers upward like this, and my thumb is pointing that way to the negative y-axis. It's the opposite of the other 16 pounds pointing down. So negative BZ times 2 feet. Then we have the last one, CZ. It's also pointing up, so it's negative CZ times 4 feet equals 0. Now we'll do the other equations. sum of forces in the x direction equals 0. In the x direction, we only have ax. These other forces are not in the x direction. So ax equals 0. Sum of forces in the y direction, that shows that ay equals 0. That's the only force in the y direction. And then az is in the z direction. So we have sum of forces in the z. That will be az plus bz plus cz minus 16 equals 0. So CZ, BZ, and AZ point up, and then 16 points down. If you solve these equations, so equation 1, equation 2, equation 3, using a system of equations. So let's say we solve for AZ and then substitute it into the other AZ position of somewhere else, or plug in BZ, solve for BZ, plug it into these other equations, or you can do adding the equations up like in algebra. So we'll get like this one, negative 16 plus CZ plus 2BZ equals 0. 32 minus 2BZ. Actually, I'll line minus 4CZ equals 0. And the last one, AZ plus BZ CZ equals 0. Solve this, and you end up with AZ equals BZ equals CZ, and then all of those will be equivalent to 5.33 pounds. So there we solved using the right hand rule for moments, taking it along an axis, and then using algebra to solve it for 5.33 pounds for AZ, BZ, and CZ.